As we begin Unit 2, we're going to start by looking at derivative graphs. We know at this point how to find the derivative algebraically for some specific functions. We don't know every function, we just know a few. But what we do know, or what we take away from the derivative, is that it will help us find the value of the slope of the curve at a point. Likewise, the slope of the curve tells us what the value of the derivative is. So we can kind of read that back and forth. The derivative gives us the slope of the curve, or the slope of the curve will give us a piece of the derivative. Okay, and we're going to use this idea to help us sketch the shape of the derivative graph. So the idea today is, given the graph of f of x, sketch the graph of its derivative f prime of x. That started to look like f double prime. Okay. All right, so I highly suggest two things, actually. So go ahead and pause the video. I suggest two things. I suggest a different color. So whether you have a colored pencil or a colored pen, crayon, I suppose highlighter. So I suggest a different color. And in a little bit, you'll need a straight edge. I highly recommend a piece of uncooked spaghetti. That's what I'll be using today. It's linguine. That's all I had. You could also use a toothpick. Or you could use, just a straight edge. You could grab a Post-it note, or just a piece of scrap paper would work as well. So something straight that we can use as a line. Okay, so you'll need two things: a different color, and you'll need some sort of straight edge. Okay, we won't need that quite yet. So it says, shown below are two linear functions. In a different color, draw the graph of its derivative. Okay, so we could do this a couple of different ways. Again, this is like two different problems on one page. So what I'm thinking is, remember, the derivative means slope. So if I start, say, and I look at this point here, I'm thinking, what is the slope at that point? Well, gosh, this line, it looks like we're going down 2/1. So I'd say the slope there is -2. If I look, say, at this point, I mean, it's a line, so once I find the slope, it's always the same thing from this point. So if the slope is, that means the derivative equals -2, which we could even write y prime equals -2. So I'm going to switch colors here. I'll use purple. So I'm going to sketch the derivative. It's just the graph y equals -2. Okay. Which we could certainly check that algebraically. Let's write the equation of the line. The y-intercept is -2 and the slope is -2. So the equation of the line is -2x plus 2. And if we take the derivative algebraically, we get -2, so that should check out. Okay. When we take a look at the next one, I'm going to do this one much faster. Same idea, I could look at any point. The slope of the function at that point is 0. The slope of the function at that point is 0. Anywhere I look, the slope is 0. So the derivative is 0, or y prime equals 0. So for every x value, the slope is always 0, the derivative is always 0. Okay? Good. Lines are easy, right? Calculus, lines, we don't really, it's like an Algebra 1 question. Well, let's take a look at this one. We've got a little piecewise graph. Good news is it's still made up of different lines. So I'm not going to draw a bunch of points, but what I am going to do is come in here and say, well, Let's look at this segment here. Looks like the slope for this entire segment is -1. It looks like the slope for this entire segment is +1. Looks like this one goes down. Looks like the slope here is -4. And then the slope here is 0. Again, because it's linear, I just look at each piece there. So, one other thing, there is a corner at -3, so let's not differentiable. So I'm going to say the derivative does not exist. That says D-E-R-I-V, if you can really read my handwriting. Let's go ahead and just write it out. Because there's a corner. There's a discontinuity here, so the derivative does not exist at 1. And there's a hole at 3, so the derivative does not exist there as well. Okay. All right, so let's go in and draw our derivative. Between -5 and -3, the slope is -1, so the derivative is -1. But remember, we said the derivative does not exist at -3, so I have an open circle there. From -3 to 1, the slope is +1. But again, I can't use -3, and we can't use +1, so put an open circle there. Then our slope is -4, and that is happening between what, 1 and 3? So from 1 to 3, my derivative is -4. And then from 3 to 6, my slope is 0, but I can't include the 3. Okay. Now the ends are kind of a different story. They're not a corner. We can go ahead and include those endpoints because they're filled in there. I don't think that will ever come up as being an issue, so we'll just leave those alone. But the biggest ones are, we definitely cannot include anything at -3, 1, and +3. Okay. All right, so I need you to grab your piece of spaghetti, your toothpick, your straight edge, because now we're going to use it. So pause if you need to. Now, you don't have this in front of you, but what I've done is I've just created 2 graphs. Let me tilt this back up a little bit. I've created 2 graphs, and I have drawn tangent lines to the graphs at 2 different points, right? So 2 different ones. So this is essentially what we're going to be doing for the next few minutes. So we had our graph, and then I drew in the tangent line when x equals 2. My question is, what is the slope of the tangent line? That's an Algebra 1 question, right? It's a line, and if we want to calculate slope, we just need to draw our slope triangle, and you can draw a variety of slope triangles, right? To me, I'm definitely going to use that point because the line goes through that point, and it looks like another integer point that this line goes through is 3, 7, right? So I could draw my slope triangle here. So I'm going up 2 and over 1. Or maybe I said, oh, definitely starting here, and it definitely goes through the y-axis at 1. So you could have drawn this slope triangle, which is up 4 and over 2, which is the same, right? A slope of 4 over 2 versus a slope of 2 over 1, right? They both reduce to 2. So when I talk about our tangent lines today and I say, what is the slope? You're going to kind of use the grid that's back there and just find 2 key points that you can use to make your slope triangle. What about this graph here? Again, some sort of maybe sinusoidal or some sort of cubic, doesn't matter. I went ahead and drew in the tangent line at that purple point. I would like to know what is the slope of this tangent line. So I just want you to eyeball, you know, honestly, a couple different things you could do, but I just want to find the nicest point that it looks like it goes through. This is an estimation, by the way. So it looks like the nicest place where it goes through those crosshairs is at 5, 1. So my slope triangle, it looks like we're going to go down 1, 2, 3, 4, 5. n over 3. So I'd say the slope of that blue line is negative 5/3. So today, as I start talking about what is the slope of your tangent line, this is the idea that we're thinking. Okay. All right. So it says for each graph, sketch its derivative by estimating the slope of the tangent line for at least 4 different values of x. I'll probably use 5. Okay. Here's what I'd like you to do. I would like you to pick 5 points that this graph goes through. I'd say some nice points. Let's spread them out. I like the vertex. I like the symmetry there. Maybe when x equals 3, it looks like the point 3, negative 4. Maybe you like the point 6, 1. I'm just going to use symmetry, and it's not perfect, but those are I picked 5. It says at least 4. Those are my 5 points. So I'm going to come over here and make myself a little t-chart, and it's going to be x and the slope, which, remember, slope means y prime. So my x's are negative 6, negative 3, 0, 3, 6. All right, here's where the spaghetti or your toothpick comes in. You don't need the entire piece of spaghetti. You can certainly kind of break it in half. This linguine is a little thick, but I'm going to start when x equals negative 6. I'm going to lay my linguine down like a tangent line, very similar to what we saw on that shape. In fact, I'm going to kind of lay it flat here so you can, okay. So you just want to kind of grace the curve, just lay it right next to it there. That's about as good as it's going to get. Doesn't have to be anything fancy. We're looking for, is it steep? Is it not so steep? And is it positive or is it negative? So when I look at this graph, it goes through this point, and maybe another point that this line goes through is maybe this one. So I'm going to say we're going down 1, 2, 3, 4, and over 2. So at that first point, I'm estimating the slope to be negative 2. Doesn't have to be perfect. It's kind of steep, and it's negative. Okay. Let's go look at our next x value. Our next x value is negative 3, so I'll put my tangent line there. So even if you wanted to use a straight and kind of draw a tangent line, maybe that would help us here. And so it looks like go through this point, and I don't know, maybe that point down 1, 2, 3, 4, and over 3. So negative 4/3, or like negative 1 1/3. Ish. You must have negative 1. Let's look at 0. Let's lay that tangent line down at 0. Looks like the slope is 0. And the graph is symmetric, so let's use that symmetry, right? That would tell us that the slope on this side is positive 1 1/3. And then the slope at 6 would be positive 2. So all we've done is to take our spaghetti, our toothpick, our straight edge, and we've laid down little tangent lines and just jotted down those slopes. So now I'm going to go in with my red pen. I'm going to plot these points. When x is negative 6, the derivative is negative 2. So I'm going to plot these points. When x is negative 3, the slope, or the derivative, is negative 1 1/3. Then I have the point 0, 0. Then I have positive 3, 1 1/3. And then I have 6, 2. So we're just going to look at those red dots. We're just going to connect them as best we can. And it looks like some sort of linear function. It's close, right? Which, let's think about it, kind of makes sense, right? And now this is not going to be perfect, but if this is y equals, say, I don't know what the constant is, but x squared, what, minus 6? Then derivative algebraically would be 2ax and then 0, right? So it's a linear function. The derivative is linear, and we see it in our graph. Okay. All right, let's flip it over and do this with a different graph. Okay. So again, I'm going to make that t-chart. Whoops, I'm going to make that t-chart so we can draw the derivative. I'm going to pick 5 or so x values, and I'm going to find their slopes, which again is the value of the derivative. Okay, so let's use our pen to pick some points here. You know what? I like this point at -4. Something interesting is happening in the graph. I like something around 3-ish, 3 or 4, 3.5, estimate it. I kind of like this point, -1, 3, because it's a nice point. The graph looks like it goes through that point. I kind of like the x-intercept. It's a nice integer, -7, 0, and maybe also 5. So I'm going to do -7, -4, -1, 3, and 5. You could pick different x values. That is completely up to you. All right, so here I go. I'm going to lay my linguini down. This is my tangent line. And I'm going to start back here at -7. And if you want to sketch it in with your pencil, that's fine. If you just want to look at your spaghetti and estimate. But this line goes through this point and let's say this point up here. 1, 2, 3, 4, and over 1. So I'm going to say the slope there is 4. Okay. Up here, when I lay my linguini down, it looks like the slope is going to be 0. Great, but let's go to -1. And you can pause this if you want to do some of these on your own. I'm going to lay that tangent line down right there when x equals -1. Maybe draw in that tangent line, so a ruler would be fine. So the line goes through that point, and I even think it maybe goes through that point. 1, 2, 3. So -1.5, -3/2. At 3, I would say we're darn close to 0. And then let's take a look at x equals 5. Let's lay down that tangent line. Kind of finagle it a little bit. Again, these are estimates. And let's look at the slope of this line. I'm going to say, I mean, it's pretty close. Let's go up 1, 2, 3, 4, 5, and over 3, so 5/3, so 1 2/3. Again, you might have 2, you might have something closer to 1, 1.5. That's fine. So let's go in and go plot these points. So I have the point -7, 4. I have the point -4, 0. -1, -1.5. I have 3, 0. And then I have 5, almost to 2. So if you kind of step back and we do a little bit of thinking here, connect them as smoothly as we can. That's the shape I saw with those 5 points. And let's be honest, it kind of makes sense, right? My original graph looks like some sort of cubic, so its derivative should look like some sort of quadratic. So this shape does not surprise us. Okay. At this point, I encourage you to pause the video and try the last 3 on your own. And then go ahead and unpause and just kind of catch up. You can fast forward to where I've drawn. I'm going to stop using the spaghetti. So if you'd like to see what that looks like, maybe stick with me just for another minute. All right. So I'm going to pick some key points here. I really like this point at 4. I actually really like this x value at like -4. Something interesting going on there. I like the point 1, -1. Maybe the point 7, 4. And I don't know, maybe like negative, I don't know, let's do -7, 5-ish. Close enough. All right, so again, I'm going to do this without the spaghetti. I'm going to just lightly with my pencil just say, what is the approximate slope there? It's not perfect, but it looks like maybe -3. Oops, I forgot to write my x values down. So we're using -7, -4, 1, 4, and 7. So what did we say? -3, -7. I laid on a tangent line there. Pretty flat. I'd say pretty close to 0. if I were to draw in a tangent line at 1, I'd say it's pretty darn close to -1. At 4, I'd say we're 0. And then at 7, that's pretty steep. It's steeper than the one over here. 1, 2, 3, 4, 5, like maybe -6. An estimation, right? All right, let's go plot these points. So I have -7, -3. I have -4, 0. I have 1, -1. So let's make that a little more red. I have 4, 0. And I have 7, -6. Oh my goodness, that's not a negative. Something stop me. That was a +6. I was just counting backwards. That's my fault. So 7, 1, 2, 3, 4, 5, 6. Okay. So when I look at my points, -0, -0, positive. Yeah, I know it's not a lot to go on, but if I were to connect these as smooth as I can, well, I missed that point, but I think we get the idea. Looks something like that. Okay. All right. Let's go take a look at this one down here. Ooh, I love the symmetry here. I like all these maxes and mins. Let's pick -8, -4, 0, 4, and 8. I like that. I think that's going to get us a good start. However, so I also like -6, -2. I like the x-intercepts because it's kind of like a halfway. -8, -6, -4, -2. I'm picking a lot. 0, 2, all of these down. That's okay. So the slope at -8 is 0. So I'm just going to go directly and plot that point. I'm going to grab my pencil. At -6, if I were to lay my piece of spaghetti down, I would say maybe 1, 2, 3, maybe -3. I think that's about right. So at -6, my slope is -3. At 4, my slope is 0 again. Good news is we get to speed this up because look at all the symmetry. If the slope here we said was -3, then I would say the slope on the other side is going to be +3. So when x is -2, the derivative is +3. We're back to 0. Now to me it's all just symmetry, right? It's the same graph, it's periodic. +3 and 0. And smooth. I had what looked like a periodic graph. It does not surprise me that its derivative is also periodic. That repetition continues on. All right, let's do the last one. All right, let's pick some key points here. There's not a lot changing in the graph. You know, I kind of like, well, let's call that -5, 5-ish. Maybe -1. Let's look at 0. Let's look at 1. And let's look at 5. It's close enough. So again, we can think about that spaghetti. And I would say the slope of that line I just drew, just put the lid on my marker here. I would say from here to say here, it looks like down 1/3. So how about -1/3? Let's take a look at -1. There's my tangent line there. Oh. But -1, my slope's -1. Let's take a look at 0. Even get my spaghetti back out. If I were to lay a tangent line there, I mean, it's just, you know, kind of follows the curve there. It looks like a vertical line. This is a vertical tangent line, right? The derivative does not exist there. But what I want to talk about is what's happening as we get closer and closer and closer. So way out here, the slope is flat. And as we move along, the graph is getting steeper and steeper and steeper and steeper and steeper until it's vertical, which means just to the left of 0, I have a negative slope, but it's really, really, really steep. This will keep getting flatter and flatter and flatter, so I said my slope is going to get closer and closer to 0. Good. Now let's take a look at the other side. Using symmetry, because this graph has a lot, it looks like that slope is -1. And let's say that slope is that -1/3 also. So, and at, what do we use, 5, we're at -1/3. And the same thing is going to be true. It's going to keep getting flatter out to the edge. But as I approach that vertical tangent, the slope gets very, 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 very steep. In fact, that's the idea behind a vertical tangent, or it's what's behind, the idea of not having slope. It's almost like the slope is infinite. The slope is super big. And so that's why we're going to go down forever. So the derivative does not exist at x equals 0 because we had a vertical tangent at x equals 0. So we have a vertical asymptote in the derivative.